Now, okay, so we're doing a recording on the beginning of the section 3.4 notes. So this is an application of derivatives, velocity, acceleration, rates of change in general. So we read this out loud. In this section, we examine application which derivatives represent rates at which things change, right? We've kind of talked about that, like, looking at derivatives of slope, and the slope to a change, right? Like that Twitter example we did, I think in section 2.4. For example, change in the cost of manufactured items per item under given conditions, right? Like, for example, if you own a company and you want to know, if you make like 2,000 items, what will be the cost per item, right? Sometimes that might change if you made 10,000 items. Or maybe we're looking at the change in volume of something, like a spherical balloon, or the change in distance from a given point per unit time. But just some things to keep in mind before we get into some real life problems. Average rate of change is just a slope, right? That's just a slope of a secant line. Easy peasy, right? So if you're looking at from a to a plus h, same thing. Just take the difference in the y values, divide by the difference in the x values. Now remember, in the instantaneous rate of change, that's the slope of a tangent line. We know that to be simply our derivative, right? Slope of a tangent line is that. So just some things that we've already discussed often. Okay. So let's keep moving. And when we use the word instantaneous, just keep in mind, x doesn't always have to represent time. Even though we'll probably think of it that way, it doesn't always have to be. For example, say a problem asks you to find the instantaneous rate of change in the volume of a spherical balloon when the radius equals 2 centimeters. So what's going to happen, I'm looking at the change in volume over the change in radius. So I want to know how the volume is changing at a particular radius value, not at a time value. And volume, as you guys should know, is in cubic units, like cubic centimeters, for example, if we're using centimeters for the radius. So your units would just be cubic centimeters in that case, or it would be the change in cubic centimeters per centimeter change in radius. And just so you know, sometimes the word instantaneous is often omitted and just assumed. So if you're asking for a rate of change, assume a derivative. If I said, hey, what's the rate of change of cars entering the freeway? Assume that to be a derivative. So let's look at example 1. And we'll revisit the volume example again. So write the volume of a sphere as a function of its radius r. Now, if you don't remember solid geometry forms, don't worry. I don't expect you guys to memorize them. You can look them up or I'll give them to you. But it is this, 4/3 pi r cubed. That's the volume of the sphere. Now find the instantaneous rate of change of volume with respect to r. So what this means is that you're taking the derivative like this. You're not using x because we have r instead. So you're taking the derivative of the volume, which means you're taking the derivative of 4/3 pi r cubed. Now, the whole notation thing, like, here we have an r, here we have an r. What if those letters are different? We're going to talk about that later in the scene. We'll do that in November. But for now, just whatever letter you see, just treat it like x and just do your power rule. So it's going to be 4/3 times pi times 3r squared. Or if you clean it up, that's 4 pi r squared. Does anyone recognize what that formula represents for a sphere? If I remember some it's surface area.
Oh.
It's okay. You're Kind of close. Well, actually, think of, well, actually, no, I'm actually glad you brought that up. Because what is area of a circle? Pi r squared. What if you took the derivative of the area with respect to r? You get 2 pi r. It's kind of interesting, right? Like the circumference is the derivative area. The surface area is derivative volume. These are things we're going to explore in more detail when we get to our 4th unit. But a lot of geometry formulas, calculus can be used to explain why they work. But again, I'm not going to kind of get too deep into that because now I'll be getting too theoretical, and I don't want to do too much theory today. Not really on this unit. The 4th unit is going to be more theoretical, and that's why I said in December, those 3 weeks in December, I'm only going to do 1 section per week because there's a lot of theory in those sections. But this is all mechanical stuff, so I can do 1 section per class meeting. Okay, so we got all that stuff there. Now, you're asked to evaluate this rate of change for different radius values. For example, b prime 1 is just going to be 4 pi times 1 squared, or 4 pi. And you're going to say it's it changes 4 pi cubic centimeters per centimeter. So what this means is that when r equals 1, the volume changes by 4 pi cubic centimeters. So for example, what if you looked at the radius when it was like 0.99 and then you go to 1? So that change from 0.99, like if you're blowing, like, actually I should probably video this. My son loves one of these, weird kind of glow in the dark bubble things. And it's kind of weird. You have to use like some sort of cream, like you insert like this little like straw thing, you blow into it and expand. And of course, we notice the expansion gets faster as it gets bigger. The expansion is not consistent actually. Like if I'm blowing into it, it's kind of slow. Then as it gets bigger, it starts increasing. And my son gets really excited when he sees that. But you know, from like 1 radius of 0.99 to 1, that's kind of the change in the volume. But then when the volume changes but when the radius gets even bigger, hold on, Catherine. So v prime of 3, that's going to be 36 pi. That's how the volume changes at a radius of 3. 36 pi cubic centimeters per centimeter. Catherine, go ahead.
When you found v prime of 1, the units were centimeters cubed over centimeters, but then you said when the radius equals 1, the volume changes by 4 pi centimeters cubed. Is that also over centimeters, or is it just centimeters cubed?
No, what I'm trying to say here, no, it's centimeters cubed still. So this right here is covered in those words right there. So I guess the best way of saying it is, actually, you know what? Let me rephrase that, because I actually didn't, I didn't finish my explanation quite well. So let me, I can sense the confusion. So what you would say is that when r equals 1, the volume changes by 4 pi cubic centimeters for a 1 centimeter change in radius. That's what I should have said. Because it's 4 pi cubic centimeters per centimeter of radius. So when r equals 1, the volume changes by 4 pi cubic centimeters for a 1 centimeter change in radius. And then for this one, for 36 pi, so what this means, if I just simply replace this stuff, r equals 3, the volume changes by 36 pi cubic centimeters. So when you have a radius of 3, now the volume changes by that much for every centimeter change in radius. So that's what we expect there. So yeah, basically, when it goes up by 1 centimeter from before, it changed by that much in terms of volume. And actually, what I should have said for the first scenario, at r equals 1, so when the radius was initially 0 and then it goes to 1, it changed by 4 pi. You can kind of think of it that way in some ways. Okay, let's now talk about linear motion. Now consider an object moving along a line where its position s on the line as a function of time t is given by s of t. Suppose s is measured in miles and t in hours. And the graph of s against t is drawn. The slope at t is calculated. Find the units of the slope. Okay. So trying to think of how I want to do this graph. Give me one sec here. I think I just want to do a straight line, but let me just look at some other notes. Give me one sec, guys. No, I'm just going to do some kind of general. Okay. So first off, yeah, let me just draw kind of just a funky curve. So you have a curve like that. So position, remember, is how far you are from something. Like, let's say, for example, this is the position you are from Sickard Prep. Say you live in Redwood City. Then you'd be about 5 miles from Sickard Prep. But then as time passes, maybe you decide to go north. Maybe you're going to Lake Tahoe or something like that, or San Francisco. Obviously, your distance from Sickard Prep would increase, right? Your position. Now, what if I drew a tangent line at x equals 2? Or t equals 2? What do you think the units would be for the slope here?
Miles per hour.
Miles per hour, exactly. Because remember, slope is change y or change in x. So it'd be miles per hour. And when you think of miles per hour, what does that represent physically?
Your speed.
Speed, exactly, yeah. And for those who follow baseball, if you look at the speed of someone's pitch. By the way, if anyone watched the World Series, I was absolutely beside myself. They pulled that pitcher out. I'm sure some of you guys might have heard of that. He was throwing some really fast pitches, but we're driving. If you get speeding tickets, like I have, and actually it would be kind of a fun thing to, if you go to County San Mateo and type in my name, you'll probably see I think it's public, or maybe you have to type in my driver's license number, but I actually have quite a bit of speeding tickets over the last 10, 15 years. But speed, right, miles per hour, you know that. And I digress. Anyway, the slope at t equals 2 represents instantaneous rate of change. So that's a derivative. The position function with respect to t and its instantaneous velocity. So it's going to represent velocity, because velocity, just so you know, has direction and magnitude. Because, for example, what if I'm driving, so say you're in Redwood City, so you're north of Sacred Heart Prep, and you're going, north towards San Francisco, so that's a certain direction you're going, right? And you could go 40, 50 miles per hour. So you take El Camino, right, the whole way. Or what if you go south? What if you're now going towards Sacred Heart Prep? You would still go at the same speed, but now you change your direction. So just so you know, speed is just magnitude, no direction. But velocity has direction. So like, for example, my velocity could be negative, if I go in the opposite direction. So that's why we tend to use velocity for derivatives of a position, because they involve direction. But I'll get into all that stuff a little later. Now, to find the average velocity, let's say you look at like t as a certain time. So say you got your position function again, this is s, this is t. You can call this like t. You can call this t plus h. So if I were to draw 2 points there and draw a line connecting those 2 points, that slope is an average rate of change. So that right there is an average rate of change. And you can do s of t plus h minus s of t over h, or remember f of b minus f over b minus a. So this is the average velocity. But how do I make this an instantaneous velocity? You assume h approaches 0. So in order to, so you basically just use the same method, same method discussed in the 2.4 notes. So in 2.4, remember we talked about average rates of change. We talked about secant lines, and eventually that secant line became a tangent line. You kind of do the same thing, right? Like if this is your average velocity right here, and if I take the limit of that as h approaches 0, now that's going to be my instantaneous velocity, or ds over dt. Now we're going to do an example down below. And then probably we'll kind of see where we are with time. Yeah, because this example is going to take a while. This example's got 14 parts. All right, fun. But they're pretty fast. And then if we have some time at the end, maybe we'll have you guys work on page 4 in breakout session. We'll come back and talk about it, and I'll do a video on the last 2 pages of these notes. Okay. So let's begin. And buckle up, no pun intended. All right, so we'll get to this example in just a second. But again, conserve velocity, v against time. Now we found the slope of this graph t equals 2. So again, what are the units of the slope? So let's look at a different graph. So this is a velocity graph now. Let's say your velocity does this. So you're comparing velocity versus time now, not position versus time. So consider a graph of velocity versus time. And you want to find the slope at x equals 2. So maybe initially you start with a certain speed, and then you're curious to see how your speed changes. Now, when you're speeding up, what do we call that? Does anyone know what that's called in physics when you're speeding up?
Acceleration.
Exactly. How about if you're slowing down?
Deceleration.
Deceleration, right, like when you hit the brakes. Now, when you hit the brakes, are you still moving forward? Absolutely. You totally are. And we're going to talk about all that stuff too. But you're slowing down, right? Now, what are the units for this slope? That's going to be miles per hour over hours. Because essentially what you're doing is you're doing miles over hours divided by hours, which becomes miles per hour squared. That's a division symbol. Sorry about that. And was represent, of course, acceleration. So to do that, to find the instantaneous acceleration, you got to take the derivative of velocity or do a second derivative of position. So second derivatives are a big deal. And some of you write like this. So that means you got to do two derivatives of the position function to get the velocity. Sorry, to get the acceleration. And I did kind of talk about this a few minutes ago. Velocity can be positive or negative since it reflects direction, but speed has no direction. So it's always a positive value. So I would love for, well, first of all, I hope none of you ever get a ticket, but I'd love for you guys to argue if cops pull you over like El Camino. Usually, sometimes I've seen cops on El Camino near Sacred Heart, near Menlo College. I've been caught there, I think, a couple times. And you know, if you said, oh, you know, you were speeding, blah blah blah, like, and I say, no, my velocity, I'm going towards Sacred Heart, and that's a negative velocity, so I'm actually under the speed. Don't try that argument. Cop will just write you a ticket and think you're a smart ass. So, by the way, if you ever want to get out of a ticket, apologize. That's all you have to do. Roll down the window, be calm, have your license and insurance ready, look the officer in the eye and say, I'm totally sorry. I just, you know, did not mean to do it. And if you have a clean record, usually they'll let you go. But just be calm. That's how you get out of a ticket. I've got several myself. So if you're curious, that's how you do it. Unless you're going really, really fast, or if you're in a Hodunk County in Highway 5, where that's their means of revenue, you're kind of screwed. I'll be honest with you. Then you hope the boss will write you down for a lower speed limit, or lower speed, so that you don't pay as much money. But okay, so it's always fun discussions about. I have a perfect record, by the way. My insurance is really low. I'm 42 years old, and fortunately, I now have good insurance premiums. Okay, example 2. This is one of the 14 parts. So we have a position function. We're going to work this function often. And you're told you're moving the line, a particle, so like a little dot. It's moving a line, and it kind of does a bunch of weird stuff. In fact, actually, the graph of the position is right here. So if you were to plug in 0 into this, our function is actually it's written two ways: a factor form and standard form. If you plug in 0, position is 0, right? If you plug in 0 for t, if you plug in 1 for t, I believe you get 4. Yep. And if you plug in other values, you get all these different values. So you get the shape here. So all we're going to do is just kind of evaluate this: s of 1, s of 2, s of 3, s of 4. I told you these parts are going to be pretty fast. So s of 1 is easy. That's just going to be 4. S of 2, if you were to calculate that, that's going to be 8 minus 24 plus 27. God, I can't do math today. Plus 18, my bad. That's going to equal 2. If you plug in 3, 27 minus 54 plus 27, 0. You plug in 4, 64 minus 96 plus 36, you get 4. That's just easy. It's plug and chug, right? I'm not too worried about that. You guys are going to be fine with that. Okay, any questions so far about what we just did? Just plug it in, right? And the points are plotted right here, right? 0, 4, 2, 0, and back to 4. Now, what is the displacement in the first 4 seconds? Now, displacement, just so you know, is represented as a change in position. So I always kind of like to, if I were to kind of get up, right? Let's say my position from the table is I don't know, right now it's a foot, right? And if I walk, I'm 3 feet away from the table. My change of position was actually 2 feet. So that's just all it is. It's not necessarily the distance you've traveled so much. It's really more, I mean, it could be the same too. But it's really just going to be your change of position. So if you're like 1 foot away from something, now you're 10 foot away from it. That's 9 feet. Now, here's where it gets interesting. So I'm saying 1 foot away from my table. I walk maybe 2 feet, and I walk back. What's my change of position now? 0, right? But I walk 4 feet, 2, right? So like if you have like a Fitbit or like some sort of device on your phone or wearable that tracks your steps, you know, it doesn't know calculus. It just knows your distance you traveled because I'm burning calories as I'm moving, right? But displacement is simply changing position. So for the first 4 seconds, I'm doing S of 4 minus S of 0. So my position at 4, of course, was, and during the first 4 seconds, hold on a sec. Yeah, so it's just going to be 4 minus 0, or 4 meters. Now, what's my average velocity? That's going to be this. That's going to be the slope of that secant line. Which is 1 meter per second. What's the instantaneous velocity at t equals 4? Now that's going to be a derivative. Okay, I did a poor job drawing that, but that's going to be a derivative. So all I need to do here is find s prime of t. Well, s was t cubed, remember. T cubed minus 6t squared plus 9. So it's 3t squared minus 12t plus 0. If I plug in 4, three times 16 is 48 minus 48. Wait, I did something incorrectly. Hold on. Oh, I'm a total moron. Okay, what did I do wrong, guys? Did I copy the position function correctly?
I think there's a T after 9.
Yeah, I forgot. Yep. And so how do I know I made a mistake? Because I was going to get a derivative of 0. That's not a slope of 0. That tangent line, that's a pretty steep slope. So I know I made a mistake. That's why you have to think about these graphically. This is why I've stressed that so much with you guys this whole year. You got to make those graphical algebraic connections because I'm doing things algebraically here, and then I realize it's not confirming what I see graphically. So somewhere, something's wrong. I know the graph's not wrong. So I'm a human. I made an error. I copied things wrong. That happens. It's okay. But that's how you catch yourself. So that needs to be rectified. So that's plus 9. Okay, so now I got my instantaneous speed. It's 9 meters per second. That makes a little more sense. That's a pretty steep slope at t equals 4. Catherine, go ahead.
Why did you use like the t cubed minus 6t squared plus 9t instead of t times t minus 3 squared?
Way
like
easier to do the derivative this way in standard form.
Okay.
You could have done the other one, but you'd have to do a product rule.
Okay, got it.
Yeah, I mean, you can. You'll still get the same thing. It's just easier. So you do want to be flexible also with the different ways you express your equations. There will be times, and we'll talk about that down the road. There'll be times where actually it would be advantageous to use a factor form. For now, because we know power rule, and I know power rule is less arduous than product rule, I'm going to use the standard form, just easier. So you do have to be somewhat versatile with. It's kind of like you guys ever watch a British baking show or any of those cooking shows? My wife is totally into it, and so yeah, actually tomorrow is the next episode, right? I'm actually kind of like, I honestly, I do my fantasy football research. My wife's watching it, but I kind of watch in the background. It's kind of interesting. But you have to be versatile, right? Like they ask me to make all these different things. You can go about making something a certain way, but then they say you got to do this also. So you got to be able to be able to mix things up a little bit and try different things, right? So sometimes like I'm trying to think of a good example. I don't really bake, but there are certain ways, like certain times where you would like, if you're cooking, you do it one way, but maybe you might try a different way if there's a different scenario that you're trying to do. Okay, well, since velocity t equals 2, that's gonna be easy. That's just s prime of 2. And remember, s prime t, we already established was 3t squared minus 12t plus 9. So it'd be negative 3 meters per second, which totally makes sense because remember our graph looked like this. Oh, yikes. At t equals 2, that's a negative slope. So now this is getting closer to the initial position. So it's going the opposite direction. So that would make sense. Now, what's the speed at 2, however? The speed is going to be the absolute value of your velocity. So it's going to be 3 meters per second. By the way, you can use a v if you want for velocity. You don't have to use s prime, but s prime means v of t equals s prime of t. And by the way, acceleration will be v prime of t, which is s double prime of t. Because we are going to talk about that as well later in this problem. But speed is always a positive value. So it's just the absolute value of velocity. Okay, any questions before we move on to J, K, M, and an O? And we won't do page 4. I just realized we don't have enough time to do that. So that will be done in the video as well as the other 2 pages. So I'll have that. I might try to do it during my breaks or during my lunch hour. So anyway, then I'll sketch velocity versus time. So basically just sketching that, right? So obviously if I make a table, that should be easy to do this. So if I plug in 0, I get 9. If I plug in 1, I get 0. If I plug in 2, I get negative 3, I think. Yeah, because you get 4, 12. 12, no, of course, yeah, you get negative 3. If I plug in 3, I get 0. Remember, I'm plugging into this, the velocity function. So the velocity function looks like this. Remember, we talked about graphing derivatives from the original. Like the original graph was this. And initially, our slope was positive up until t equals 1. Then our slope was negative until t equals 3, actually. And it goes back to being positive again. I actually should extend this out a bit more. There we go. So the sketch is done. So when does a particle change direction? It changes direction at t equals 1 and 3 seconds. Because velocity changes sign. When the velocity goes from positive to negative or negative to positive, that's when you change direction. I mean, you could see it from the graph of the original. If I redo the graph of the original, I'll do it one more time down here. I mean, duh, obviously it changed at 1 and changed at 3, right? It was going away, then it's going back, and it's going away at 3. But the velocity graph could be a little bit more revealing, because you see at t equals 1, yeah, it was positive velocity, now it's negative velocity. And at 3, it's negative velocity, now it's positive velocity. And what's velocity at these times? Of course, 0 meters per second. So you always change direction at 0. So change direction with velocity changes sign. Very, very important. Put a little star there for good reason. Any questions before we move on to the remaining parts and before we wrap up the notes here? No? Okay. So what was the acceleration at time t equals 1 and t equals 2? Now in this case, acceleration I could find by simply taking the derivative of velocity. Now remember, what was velocity again? Velocity was 3t squared minus 12t plus 9. So what's going to be my derivative of the velocity? 6t minus 12. So what's a of 1? There's 6 meters per second squared. You got to do those units. How about 2? It was going to be actually at 0 meters per second squared. So again, if we kind of look at what's going on with the velocity graph, remember the velocity graph looked like this. This is my velocity curve. So you're clearly decelerating at t equals 1, right? But then the velocity kind of stops changing at 2. Then all of a sudden you start accelerating afterwards. So that's one way you can kind of think of it from the velocity graph. The velocity is changing in a negative fashion, right? It's going down, right? Your velocity is decreasing at 1. So you do need to have a negative acceleration. But then the velocity doesn't change at 2 because it's flat. The tangent line there is flat. Then it gets increasing again. So this helps, hopefully will help enhance your understanding of the derivative and how the graphs of the derivative functions relate to each other. When is a particle velocity at 24 meters per second? Well, you could just set 24 equal to a velocity function. And solve for t. And for O, when is particle acceleration at 12? You can set 12 equal to the acceleration function. And kind of work each of these out. For O, that's easy. That's going to be 4. Wow, can't wait to do that. 6t equals 24. So 4 seconds, our acceleration is at 12 meters per second squared. However, for part N, I do have to do a little bit of factoring, so apparently, maybe, we'll see. You get -1, which is weird because you can't go back in time. So it's just 5 seconds. So I think this is kind of a good natural place to, if we had, if I didn't go over the test, I think we probably would have had time to do maybe page 4 is an activity, like maybe you guys in breakout sessions. So I would suggest that you perhaps try page 4, like before you watch a video, maybe try it on your own. I might suggest you do that, and then watch a video and see how you do. And then of course there's 2 more pages after that. So I'm going to make a video. I'm going to do this 3 separate videos. Here's page 4, here's page 5, here's page 6. I'll give you guys the links for that. Actually, I might do the page 4 one right now before I teach my B period. Kind of squeeze that in, then I'll do pages 5 and 6 during lunch. And I should have the homework all ready to go by this afternoon. Also because it's my daughter's birthday today, so I'll be busy tonight. So, and then tomorrow I just don't want to do any work. So, anyway, that will be the plan for homework. So it'll be 3 short videos to watch, all related to 3.4, dealing with pages 4, 5, and 6 of these notes. I obviously did a recording here, so I will upload this to Schoology. We'll upload to YouTube and share the link in Schoology pretty soon. There'll be a Google form that goes with the videos that you'll watch over the weekend. There'll be some book problems. Book problems, I'm only going to have the book problems deal with the first 3 pages of these notes. I think you guys could handle doing the practice here because I don't think this is terribly challenging. Anything that pages 4, 5, and 6 cover in the video, we'll do practice problems like that in class on Tuesday, kind of reinforce those skills. And then we'll do 3, 5 in the second half of class on Tuesday next week. So I think that's pretty much it. So look for the homework to be posted by this afternoon. And we'll just end class a couple minutes early. And you guys have a good weekend, and I will talk to you guys later.
Thank you.
Thank you.
Thank you.